Hi everybody, in this video we're going to go over the review sheet for test number 3. So the first question in part A, we're going to construct an equilateral triangle. All we have to do is measure the length of the line segment because that's going to be the measure of all three sides since equilateral triangles have three of the same sides. So I'm going to just measure it and put an arc to show I measured. Then I'm just going to use that same measurement and swing an arc on point A. And then I'm going to go over to point B and using the same measurement, I'm just going to swing the same arc. And it looks like I did not make, my first arc long enough. So I'm just going to go back over with the same measurement. And I'm just going to extend my arc a little bit further. And now that I have my arcs intersecting, I'm just going to use my straight edge and connect from point A to the intersection point and from point B to the intersection point. So how you know that you constructed an equilateral triangle? Well, you measured the length of the line segment and then you used it for all three sides. You copied the same line segment for the three different sides. That is the construction. It was copying a line segment. I'm going to write that here in a little bit smaller print. We copied the length of AB and used it for all three sides of the triangle. So we know for sure that all three sides of the triangle are the same length. It does say here, be prepared to construct scalene and isosceles triangles. So remember, there is a weekly recap video going over all of the previously learned constructions, including that one. Taking a look at number 2, whenever you're approaching any question that has a lot of complicated givens and a complicated diagram, your best course of action is to mark the given information in the diagram. And everyone always misses the givens about parallel lines, but oftentimes, especially when you're dealing with angles, they can be most important. And here, if you take a look, we do have information about angles, and we are going to be figuring out more angle measurements, so that's going to be really important. And already, if I just highlight the parallel lines, I know I didn't fill in any other angle measurements yet, and the transversal that intersects them, I already see that letter Z, and I already know, since the lines are parallel, that we have congruent alternate interior angles. There they are. So that already gives me a lot of information just from knowing I have parallel lines cut by a transversal. So don't skip that given. Parallel lines are very important, especially when it comes to angle relationships. So in triangle RAS, we already have two angles. We have 68 and 47, sorry. So we know that all three angles of any triangle must add to 180 degrees. So I'm going to add these two up and subtract from 180 degrees. And I got 65 when I did so. You can verify and do the same thing. And since we know that these two angles are congruent alternate interior angles formed by the parallel lines, I know that this angle measure is 65 as well. And now from here, it's really simple for me to find the last side of the triangle, the last angle of the triangle, my bad, I misspoke there. All I have to do is add up in triangle SAT, the 65 and the 48, and subtract from 180 because all angles in any triangle always add to 180 degrees. So I'm going to do that, and I got 67 degrees. Now remember, the longest side of a triangle is opposite from the biggest angle. Biggest side opposite biggest angle, smallest side opposite smallest angle, same sides opposite same angles. Pretty simple. Here's the biggest angle in triangle SAT, and directly across from that angle is side ST. So side ST is going to be the longest side of this triangle. Moving along over here, first we'll work on filling in the angle measurements, and then I'll show you a written up explanation. This is a Regents question, and it does say explain, and explain does mean in words. And when you are doing an explanation question on the Regents exam, you don't really receive points for what you mark in the diagram. You get points for what's in your explanation. So just be sure that everything that you're marking in the diagram, you explain in your explanation. If you're putting down an angle measurement in the diagram, you should have a reason justifying how you know that it was that angle measurement. So let's start off with filling in our given information. I know that angle EGB is 50 degrees. And I know that angle DIG is 115 degrees. And we need to explain why AB is parallel to CD. Be careful here. You don't know the lines are parallel. I saw a lot of people trying to say, oh, parallel lines, alternate interior angles are congruent. Or this is 50 degrees, so this is 50 degrees as well because they're corresponding angles. Yeah, they're corresponding angles, but you can't assume that they're congruent. And the reason for that is you don't know the lines are parallel. Those special angle relationships are only true when you have parallel lines cut by a transversal. The only angle relationships that hold regardless are vertical angles, which are always congruent, and supplementary angle relationships. Angles that form a linear pair are always supplementary to each other because they form a straight angle, a straight line. Everything else, those alternate interior, alternate exterior, same side interior, corresponding, only true when lines are parallel. Let's fill in more measurements. I know that these two angles form a linear pair. I know that for sure. So I'm going to do 180 minus 115, and I got 65 degrees right over here. And another thing that I do know for sure is that we have intersecting lines. I see my letter X. So I do have congruent vertical angles. And remember, vertical angles are really, really nice because they are always congruent to each other. Now, if you're wondering where to go from here, go back to your given information because chances are if you can't figure out your next course of action, you probably missed a given. All the givens are there for a reason. And we did miss a given. And this is one that people like to skip, but it is super important here. And that is that GH is congruent to IH. Be careful, GH is here and IH is here. I know it's super tempting to want to mark these two sides of the triangle as congruent, but that's not what it states. It states these two sides are congruent. And now let's talk about what conclusion we can draw from that. When you have a triangle with two equal sides, an isosceles triangle, the angles opposite those congruent sides are also congruent. You find the congruent angles by looking opposite the congruent sides. Here, we have the same situation. The only difference is these are the two congruent sides instead of these two. So we're going to look across opposite from the congruent sides to find the congruent angles. So we have that this angle and this angle are congruent, opposite from the congruent sides in the triangle. And that is super, super important. Let me just erase those. Because if this is 65 degrees, which we knew for sure, this here also must be 65 degrees. Now we have two angles in triangle GHI. We can add them up. 65 and 65 is 130. And we can subtract from 180 degrees. And we do get 50 degrees, like a lot of you are probably thinking at the beginning. But now we know it for sure. We're not just making things up or assuming things that might not be true. And now we know it for sure. Now we're thinking about how to show the lines are parallel. We have a ton of angle relationships. We are good to go. You can find more angle relationships, but we don't need to. A couple of options. So number one, gonna highlight parallel lines in the transversal. Notice how these two 50-degree angles are corresponding angles. They are both in the top right position where the parallel lines meet the transversal. So they are corresponding angles. We can use the fact that they're congruent to say the lines must be parallel, because if corresponding angles are congruent, then lines must be parallel. That's one of our special relationships that only holds true when we have parallel lines cut by a transversal. Another way, and this is the way that people might see a little bit more, is you could use congruent alternate interior angles. You have this pair of alternate interior angles, the 250-degree angles. You also have, well, if you were to fill in this measurement, you would have this pair. I only filled in this one, so these are the alternate interior angles I'm going to stick with. Angle AGH and angle IHG. And since those alternate interior angles are congruent, that proves that the lines AB and CD have to be parallel to each other. And now I just wanted to show you a couple of examples of full credit responses to this question. And these are full credit responses straight from the Regents exam, because I wanted you to see what a full explanation for this question would look like, explaining every piece along the way. So notice how the first thing we did together was we found this was 65 degrees because they were linear pairs. And notice how that's explained in the explanation. And the second thing we figured out, well, we figured out the vertical angles. You can put that here, but this person didn't use them, so they didn't put it here. So then they figured out that these two angles were congruent, just like we did. So notice how that's explained here. Base angles of an isosceles triangle are equal. You can also say angles across from congruent sides in a triangle are congruent. And then they explained how they found the rest of the angles as well. And this person used same side interior angles being supplementary, the 65 and the 115, to prove the lines parallel. Over here, this one's more similar to what we did because they used alternate interior angles as well. And feel free to pause the video and read their response and just notice how they explained most of their steps along the way, but they didn't explain two of the angles that they were using. And that resulted in 1 point being taken down. So you might have thought that this was going to be a full credit response because it looks like it summarizes what the person did and it might look similar to your response, but you literally have to explain where each angle measurement that you're using is coming from, else it's not full credit on the Regents exam. Because if it's an explanation question, they are literally only grading you on the explanation, not on what's in your diagram. You could know how to find all the angles. If it's not in your explanation, it doesn't matter. You don't get the full credit for it. Okay, for the next question, what we're doing is we're going to be constructing an altitude to the side of the triangle. Let me get my compass and bring it down to where it needs to be. So an altitude is just a perpendicular line through the opposite vertex of the side that you're making it to. Basically, it's a perpendicular line through a point. So I'm going to do the altitude to side BC, and that means it would have to pass through point A because A is the opposite vertex from BC. So just like with the perpendicular line through a point construction, because that's all this is, I'm going to start off by putting my compass on the point that I want my altitude, my perpendicular line, to pass through. I'm just going to open up. The exact distance doesn't matter. All I need to do is swing an arc that hits the side of the triangle in two spots. Oops, I'm going to need it a little bit bigger than that. I already see it's not going to intersect the side of the triangle. Let me open mine a little bit wider. Okay, hit it in one spot. Oh no, it doesn't hit the triangle in two spots. That's okay. We can get our straight edge and we can extend the side of the triangle slightly so that we see our two intersection points. And now I see my 1, 2 intersection points here. And that's where I'm going to put my compass next. I'm going to grab my compass. Oops, if my compass would let me grab it. And it doesn't matter the distance. And I'm just going to swing an arc. Then I'm going to go over to the other intersection point. Once again, the distance doesn't matter, but it has to be the same that you used here. So I'm not changing it. And I'll just make another arc. Through the intersection point, I'm going to connect. And it should come really close to passing right through the opposite vertex, the vertex that we had our compass point on at the beginning of this construction, because that was the point we wanted it to pass through. And here's our altitude to side BC of the triangle. Notice how it forms a right angle and it passes through the vertex. It is outside the triangle. That's because this is an obtuse triangle. The altitude should be located outside the triangle for at least some of the sides in an obtuse triangle. That's okay. Okay, so here we're making a line parallel to this one. First step is always getting the equation of the line in y equals mx plus b form so you can actually see the slope. So I'm going to subtract 4x from both sides. Then I'm going to divide everything by -2. -4 divided by -2 is just 2. 8 divided by -2 is -4. So our slope is 2, or 2/1. And we're making a parallel line. Parallel lines have same slope, so we're going to be using the same slope of 2. Now, in order to write the equation of a line, when you have a point and a slope, point-slope form is the way to go. To use it, all you need to do is plug in your slope for m and the x and y coordinate of the point that you want your line to pass through into x1 and y1. So y1 is 1 from the point we're given. The slope is 2. And -2 is x1 from the point that we're given. You can leave your answer like this. This is a full credit response. If you wanted to, you could take it a step further and actually solve for y, but it's unnecessary and you don't have to. These are equivalent equations, the one I boxed, and y equals 2x plus 8. The only difference is one is in point slope form and one is in slope intercept form. It's just two different ways of writing the same line. You can leave it as is in the box. In fact, for a short answer question, I would recommend you leaving it like that, because if you did solve for y and you made a mistake solving, you would lose a point. Okay, there's an error in question number 6. For question number 6, cross out reflexive property. There's nothing that's congruent to itself here, or nothing that's shared. And we're going to replace it with substitution. So first off, we're going to mark the diagram with our given information, which is that AC is congruent to DF, and that BC is congruent to EF. And our goal is to get AB congruent to DE. So we're going from longer segments AC and DF to shorter segments AB and DE. So that's going to be subtraction. So already I'm going to knock out choice 3 and choice 1. Now, transitive property is a special case when two things are congruent to the same third thing. So that implies they have to be congruent to each other. But this doesn't involve 3 line segments here, 3 objects. These are 4 different objects, AC, DF, BC, and EF. So there's nothing in common between these two. There's not 2 things congruent to the same third thing. So this would not be transitive property. So by process of elimination, we've narrowed it down to 2. But let's write out the subtraction to see why. In order to get AB, we're going to do AC minus BC. And that gives us AB. In order to get, I should write it over here. In order to get DF, oh, DE, my bad. I'm misreading the conclusion here. In order to get DE, we're going to do DF, the whole segment that we're given, minus EF. So this step over here is our subtraction. And then from here to here, what we're doing is we're replacing the subtraction with what it leaves us over with. And that's substitution, when you're replacing something with something that's equivalent. Substitution generally always follows the addition or subtraction postulate. Addition and subtraction often involves the reflexive property. There just wasn't anything that was being added or subtracted that was the same here. There were no 2 congruent segments to itself here, nothing overlapping or shared. So this wasn't an instance of reflexive property. This was subtraction followed by substitution to replace the subtraction with what it leaves us over with. For the next one, I highly recommend graphing. So we have 1, 2, 3, 1, 2, 3. That's A. 1, 2, 3, 4, 5, 6, 7, 9. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 3. Let me connect together. And here's my triangle ABC. Now, I need the point of intersection of the medians. Remember, a median connects midpoint to opposite vertex. This is a straight line, so I can count the boxes. 1, 2, 3, 4, 5, 6, 7, 8. So 4 units in would be the halfway point. 1, 2, 3, 4. That was easy because it was a horizontal line. And now I can just connect the midpoint to the opposite vertex. I didn't even have to use midpoint formula there. Now for one of the other sides, either AB or BC, I will have to use midpoint formula to find the midpoint. I'm just going to do AB with these 2 points. So that's 3 plus 7 over 2 and 3 plus 9 over 2. So that is 10 over 2 is 5 and 12 over 2 is 6. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. That's that point right here. You might have guessed it, but now we know for sure. There we go. And you could make the third median if you wanted to, but 2 is enough to see where they intersect. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. That is the point 7, 5. And our special name for the point of intersection of the medians is called the centroid. So the centroid of this triangle would be located here. You do need to know the special segments and what their point of intersection is. Perpendicular bisectors intersect to form the circumcenter. Altitudes intersect to form the orthocenter. Medians intersect to form the centroid. And angle bisectors intersect to form the incenter. Here we're told that P is the centroid of triangle ABC. Remember, anytime you see centroid, think that each median is being split in a 2-to-1 ratio. The longer part of the median is the 2 part of the ratio, and the shorter part of the median is the 1 part of the ratio. So here we're given that PM is the shorter part of the median is 2x plus 5, and we're given that the longer part of the median, BP, is 7x plus 4. So I'm going to set up an equation that says this is double this. If I take the smaller one and I double it, I'll get the bigger one. That's what the 2-to-1 ratio is saying. So if I take the smaller one, which is 2x plus 5, and I double it, I should wind up with the larger one. So now I'm just going to solve my equation. That's 4x plus 10 is equal to 7x plus 4. I'm going to subtract 4 from both sides, and then I'm going to subtract 4x from both sides. And what I have is 6 is equal to 3x. So x is equal to 2. And then we need to plug back in to find the length of PM. 2 times 2 is 4, plus 5 is 9. So the length of PM is 9. To double your answer, since a median is split by the centroid in a 2-to-1 ratio, EP should be 18. So if we take our x value and we plug in, 7 times 2 is 14, plus 4 is 18. This all makes sense. This is all good. We found the correct length of PM. Moving on to question number 9, we have isosceles triangle ABC. Do not miss any words. Isosceles is there for a reason. It's to tell us that this triangle has 2 equal sides. And those 2 equal sides are AB and CB. And I'm going to stop before I even look at anything else because I know something really important about isosceles triangles. I know that when a triangle has 2 equal sides, the angles opposite those sides are also congruent. The same applies here. Just think of it without the lines. The shape is the same triangle that we have right over here. So the 2 angles opposite the congruent sides are also going to be congruent. I'm going to just make that look a little bit nicer. These 2 angles will be congruent to each other because the whole big triangle is an isosceles triangle. And now I'm going to move on in the question, and I'm told that all of these segments here that I see are angle bisectors. And that's super important because that means all of the angles, are being split equally in half into congruent parts, and this one up here as well. And you might mark your diagram a little bit differently. This is just the way that I know what's equal and what's congruent. It makes sense to me. Mark your diagram in a way that's going to make sense to you without getting you confused about what's going on. So we're told the measure of angle BAC. So angle BAC is this whole angle here is 50 degrees. Oh, wait, but I knew these two angles were congruent to each other. So that means this whole angle C is 50 degrees as well. And oh, wait, that means 25 degrees and 25 degrees. And that means 25 degrees and 25 degrees. And wait, we even know more than that. Because if the two angles of triangle ABC are 50 degrees each, 50 plus 50 is 100. That leaves this angle at the top having to be 80 degrees to make that 180. And that means each of these halves is 40 degrees. Now I'm just filling stuff in here because I didn't even look at what my goal is. I should probably look at that. My goal is to find the measure of angle AXC. Angle AXC is this whole angle here. I'm done. You might be asking, how am I done? Because there's many triangles in this diagram. And I already know two angles of this triangle AXC. I already know this angle's 25 and this angle's 25. That's 50 altogether. So that means this last angle of the triangle has to be whatever will make 180 with 50. And that's 130 degrees. There we go. All done. And as you get more experience with triangles, you'll start noticing which triangles you have two angles of, and you can easily find the other angle of. When you have many different triangles inside triangles, fill in what you know, and then see which triangles you have the most information about. And those are the ones that are going to help you get to your answer. This was not the only way to reach the answer. You might have done it a different way. The answer is 130 degrees, though. Okay. Over here, there are two different ways to do this to prove that we have a right triangle. Option one is you can find the lengths of the sides of the triangle using distance formula, and then you can use Pythagorean theorem with the lengths. That's a lot of work, and I don't like to do distance formula, so I'm not even going to do that. I'm going to use slope formula because we know that if we have opposite reciprocal slopes, that means we have perpendicular lines which form 90-degree angles. You don't have to graph. It's optional always, but I'm gonna do it. I do recommend graphing, especially in our later units when we get to quadrilaterals. If you don't graph, oftentimes people make a lot of mistakes and they confuse sides with like diagonals, but that will be later on when we get to quadrilaterals. So I do highly recommend graphing always, just so you can see what you're working with. Now, hopefully I graph this correctly. And this helps me a little bit because I'm guessing here, and I know I shouldn't trust diagrams, but I'm guessing that RS and ST are the sides that are going to form the right angle. I'm going to do the slopes with those sides first and hope I get opposite reciprocals so that I don't have to find the slope of RT as well. So slope of RS. Okay, so slope is y2 minus y1 over x2 minus x1. That's -8 over 4. And I'm going to reduce because otherwise I might not see the relationship between this slope and the other slopes. And that is -2. And I'm going to just write it as -2 over 1. Now I'm going to find the slope of ST, and I'm going to hope I get some opposite reciprocals so I don't have to do the other side. And that's 2 minus -1 over 9 minus 3. That is 3 over 6. And that is 1/2. So notice, just like we expected, it worked out well. We do have opposite reciprocal slopes. So I'm going to make my concluding statement. Since RS and ST have opposite reciprocal slopes, they are perpendicular. So they form a right angle, making triangle RST a right triangle. That's a concluding statement that fully explains what my calculation showed and what I'm proving based on those calculations. Moving onwards, we're going to write the equation of the perpendicular bisector of the line segment whose endpoints are -1, 1, and 7, -5. Once again, you don't have to graph, but I'm going to do it real quick just to show you what the segment looks like. Oops, let me use a straight line to do that. So a perpendicular bisector would cut this line segment in half and would also form right angles with it. So we need two things. We need the point that it's going to pass through, which is going to be the midpoint of the line segment. And then we need the slope of the line perpendicular to this one. So first I'm going to start off with the midpoint so we can get the point that it should pass through. So I'm going to find the midpoint of the original line segment. Oh, there we go. I got to watch my signs there. 3, -2. And then we need the slope so that we can find the opposite reciprocal slope to it and get the perpendicular line. So the slope is y2 minus y1 over x2 minus x1. And in simplest form, that's -3 over 4. So the perpendicular slope that we're going to need is 4 over 3. So now that I have my slope that we're using and my point, I'm all set to write the equation of this perpendicular bisector. I'm going to use point slope form to do that because once again, it's super simple when you have a point and a slope. So I'm going to plug in the y coordinate for y1, the slope that we're using for m, and the x coordinate for x1. And you can very well leave it as is. I would recommend that you do. I'm just going to solve it for y so I can graph it so you can see what it looks like. So if I did solve for y, that would be y plus 2 equals to 4 over 3x. Minus 4. And that would be 4 over 3x minus 6. So I just want to show you what that looks like. And notice how our perpendicular bisector does pass through the midpoint and is perpendicular to the original line segment. But once again, I recommend just leaving it in the boxed version that I have it in point slope form, because if you leave it in point slope form, you avoid making a mathematical error, especially when you have fractions. That might get a bit confusing. Okay, for the next one, we are constructing the centroid. The centroid is where the perpendicular bisectors of a triangle intersect. We only need to do two sides. I'm going to put my compass on the endpoint of one side. I'm going to do this side first. And I'm going to open up about 3/4 of the way down. Doesn't matter the exact distance, just more than halfway. Then using the same distance, I'm going to go over to the other endpoint. And I'm going to make the same arc. Oh, sorry. The centroid is where the medians meet. I misspoke before. I said it's where the perpendicular bisectors meet. I meant we have to do the perpendicular bisector construction. And the perpendicular bisector construction is going to get us the midpoint of the side because we're bisecting it. And now once we have the midpoint of the side, what we actually have to do is connect the midpoint to the opposite vertex, and that's the median. So my blue segments are going to be the median. Okay. I'm going to go over to another side of the triangle and do the exact same thing. So I'll just go over to this bottom side just because I have more room here. And just like before, any distance, it doesn't matter, just more than halfway, about 3/4 of the way down the line segment. Okay, I did it on one endpoint of the side. I'm going to come over here and do the other endpoint of the side. Sorry for the large arc. It's just hard for me to move the compass on this computer. It doesn't matter as long as you have the intersection point. And there's my second perpendicular bisector of this side. And once again, the reason I needed to do a perpendicular bisector was to get the midpoint of the side. And now what I can do is I can take my midpoint and I can connect it to the opposite vertex. And that's my median, except I did a really bad job of connecting that because this is super hard on the computer. And 2 is enough to see where the medians intersect. This point over here would be the centroid. And I know it's an obtuse triangle, but centroids are always located inside the triangle, regardless of what triangle type you have, as is in center. Orthocenter and circumcenter that could end up in different locations depending on the kind of triangle that you're working with. And medians are what we used to make the centroid. Make sure you know which segments create which center. So here you actually had statements and reasons to choose from. So obviously your given information is going to go first. So I'm just going to put CD congruent to CE. That's given. I'm also going to mark it in my diagram. And so I used this and one of the givens already. I'm just going to cross them out really terribly. And then my second given is this. So I'm going to put that in my proof. And the reason is given. So DA congruent to EB. And that's given. And my goal is to prove angle 1 is congruent to angle 2. And I don't really know how I'm going to do that. So I'm going to try to use my reasons and statements bank over here to figure out a direction. So do that, we're adding something. So let me see what we're adding. We're adding CD plus DA. Oh, and that gives me CA. So this must come before this one over here. So I'm going to get that in my proof, the addition. And I know that addition postulate goes with it. So we have CD plus DA is congruent to CE plus EB. That is the addition postulate. And CD plus DA gives me CA. So that's the result. And CE plus EB gives me CB. That's the result. So I'm doing great here. And I use that one. And that's substitution. We're saying this plus this is that. This plus this is that. We're replacing the addition with what it leaves us over with. So we're doing great so far. Okay, well, there's only one choice left. And that's that angle 1 is congruent to angle 2. Let's think about why. We know from our addition that the whole big triangle ACB has 2 equal sides. That's what we just proved in step 4. That CA and CB are congruent. That's 2 sides of the big triangle. And we know that if we have an isosceles triangle, a triangle with 2 equal sides, the angles opposite those congruent sides are also congruent. So that's what's happening here. Since the sides of the triangle are congruent, just imagine it without the line in it. It'll look exactly like this one here. Since the 2 sides of the triangle are congruent, the angles opposite, which are angle 1 and 2, are also congruent. If 2 sides of a triangle are congruent, then the angles opposite those sides are also congruent. Moving on to the next one, you might remember this as the extra credit from the last test. It also has shown up in various places on different assignments, and that's because it's a really nice proof. And a lot of you guys didn't get a chance to look at it yet or do it. Some of you did. So we're given that angle 1 is congruent to angle 2, and I'm going to go ahead and mark that in the diagram. And I'm already noticing their alternate interior angles. That's actually going to help us out in a little bit. And they also tell us from the givens that angle 2 is congruent to angle 3. I'm using different colors. That's why I'm putting the same congruence mark on all of the angles, because I'm using different colors, so they're color coded. But if you're using just a pencil on the test, just make sure that you put like 2 arcs instead of 1 arc on different angles, so you know that they're congruent to each other. Okay, my first thing I need to prove is that A is parallel to B, that this line is parallel to this line. Oh, simple. Oops. As I was saying, simple enough, because I already know the alternate interior angles. Angle 1 and angle 2 are congruent, those angles in purple. If alternate interior, sorry for the terrible handwriting, angles are congruent, lines cut by a transversal are parallel. So that would prove that A is parallel to B. Right away, just from our givens. That's cool. They already gave us congruent alternate interior angles. Okay. Oh, it's saying we can prove our next proof statement right away after that in this fill in the blank proof. Let's think about why. Now we're talking about proving B and C parallel. Ooh. Angle 2 and angle 3 are corresponding angles. Top right, top right. They're corresponding angles. If corresponding angles are congruent, lines cut by a transversal are parallel. And there's something in between B parallel to C and the next thing we have to prove that A is parallel to C. Let's take a look at what that is. That angle 1 is congruent to angle 3. Well, that must come from something that we've proved earlier, or have in our proof, or have in our diagram. And I know my diagram got a bit messy, so let's take a look at our previous statements. And I'm looking for stuff about angle 1 and angle 3. Well, here's angle 3, and it's congruent to angle 2. And here's angle 1, and that was congruent to angle 2. So angle 3 and angle 1 were both congruent to the same angle 2. So that implies that they do have to be congruent to each other. And that's transitive property. If two things are congruent to the same thing, they have to be congruent to each other. They have no choice. If angle 1 and angle 3 are both congruent to angle 2, they have no choice but to be congruent to each other. And now it's telling us that we can prove A is parallel to C. So that must have something to do with angle 1 being congruent to angle 3. And know this. If I highlight lines A and C, the lines I'm proving parallel, and the transversal between them, I see a letter Z. And it turns out angle 1 and angle 3 are alternate interior angles formed by line A and line C. And if alternate interior angles are congruent, lines cut by a transversal are parallel. I'm going to put that here. If alternate interior angles are congruent, lines cut by a transversal are parallel. And then finally, the last thing that we need to prove is that angle 3 is congruent to angle 4. So I know that has to be the last step of our proof, even if I'm not sure why. And let's think about it. So now we know from step 6 that line A is parallel to line C. That's what we just proved. So this new thing that we're proving must have some relationship to A being parallel to C. Here is angle 3, and here is angle 4. And notice how these two angles are corresponding angles formed by line A and line C. Top right, where the parallel line meets the transversal, and top right, where the parallel line meets the transversal. So, since we already know that A is parallel to C, we know that angle 3 is congruent to angle 4 because corresponding angles are congruent when parallel lines are cut by a transversal. So if parallel lines are cut by a transversal, corresponding angles are congruent. See, that was not so scary.